Okay, so this is the third in a series of videos of working with reference angles. In the first video, we defined them and found them. In the second video, we used them to find exact values. And in this one, we're going to say, well, what happens if we can't actually use exact values? So all we can do in that particular case is express each in terms of a reference angle. So I'm going to take this second example. I'm just going to slide it down a little bit. So sine of negative 75 degrees. So once again, I'm going to go reference angle here. So I'm going to draw my coordinate plane with an initial ray and a terminal ray. In this case, my terminal ray will be here, and that's my angle right there. That's my angle theta. Now, my reference angle, I want to measure acutely to the x-axis. So what I have here is I see I have the same arcs, and that's okay. But since I always define my reference angle as an acute angle between 0 and 90 degrees, this is going to be at 75 degrees. So my reference angle is 75 degrees. And I'm going to take the same approach that I did in the last video with the example. I'm going to now draw the 75-degree angle on the coordinate plane. And I'm going to establish my x, my y, my r, and how the signs, S-I-G-N-S signs, relate to each other. So if I choose some point on the terminal ray with a coordinate, with coordinates x and y, and some distance r there, and then if I take that and I reflect that over the x-axis to some point here, x, y, with some radius r, I would say that as I do that, my value of x from here to here stays the same. My value of y is the opposite. In the fourth quadrant, y is negative. In the first quadrant, y is positive. And I would also say that the value of the radius would stay the same. So in this particular case, I know that I can say that sine of 75 degrees, my reference angle, is going to be some sort of positive output. Some sort of positive output. Because when I define my y over my r, I'm going to have a positive value for y, a positive value for r, and a positive divided by a positive is positive. Over in the left-hand side, where I have sine of negative 75 degrees, I know that that is going to be some sort of negative value. Because as I divide y over r, I will be dividing a negative y coordinate by a positive r value, and that will be negative. So at these two outputs, the output of sine of 75 degrees and the output of sine of negative 75 degrees are opposite to each other. So I would write that sine of negative 75 degrees is equal to the opposite of the sine of positive 75 degrees. I did not factor out a negative there. Like some people would look at that and say, oh, he factored out a negative. Man, that's not what I did. I used the reference angle. It just happened to be negative because this output would be negative and this output would be positive. So I had to make the green highlighted value negative by simply putting a negative in front of it. Now, I don't know what sine of 75 degrees is. It's not a common value. It's not 30, 60, 90. It's nothing that 45, nothing we know about. So, so we just leave it at that. We're just expressing in terms of. There's that world famous pre-calculus algebra sort of statement, in terms of. Okay? All right, so there's our first example. Our second example, we'll do the same thing in radians. I will draw my coordinate plane. I will draw my initial ray. And as I look at that angle, I see 11 pi over 5. In my head, that's how I kind of separate it. I separate the 11/5 from the pi. And I'm like, well, that's a little more than 2. 10/5 would be 2, so that's 11/5. So that means I'm going to rotate 1 full revolution plus a little bit, And that is now going to be, that's my angle, 11 pi over 5. My reference angle will be this measurement here, which means I can say, well, how far past 2 revolutions did I go? So if I take 11 pi over 5 minus 1 revolution minus 2 pi, so that's 11 pi over 5, really minus 10 pi over 5. And that's going to give me 1/5 pi. So that's my reference angle. My reference angle is pi over 5. Draw my second. Now I'm drawing all these. Eventually you'll be good enough that you're simply going to think your way through these things. I don't want you drawing these forever. I'm just kind of getting us going here. So I go to my x's. If I choose a point here, x, y with a radius. If I choose a point here, x, y with a radius. This one's actually much easier than the other one. And we can see that the x coordinate is going to be exactly the same because I don't have to reflect it. They're both first quadrant angles. The y coordinate is going to be exactly the same. And the radius is going to be exactly the same. So in this particular case, I'm going to slide some of this out of the way here. Leave a little bit of space. Sorry about that. So it's going to be exactly the same. So I can say that cosine of 11 pi over 5 is going to be exactly equal to cosine of pi over 5. Cosine being defined as x over r. These two angles, 11 pi over 5 and 1 pi over 5, have the same exact x-coordinate. They have the same exact radius. So those two functions, the two functions, this function and this function, are going to have the same exact output. I don't know what it is. If you want to test it, put it in your calculator. Put cosine of 11 pi over 5 in your calculator, hit enter, get a value. Put cosine of pi over 5 in your calculator, hit enter, get a value. And you can do this for all these, and you'll confirm that they're all going to be either the same or they are going to be opposites. All right, so a couple of examples about how you would work through using reference angles when you don't have exact values and all you want to do is express it, write one in terms of the other. And they're either going to be equal or they're going to be opposites, because when you reflect across an axis, the coordinates of the x and the y are either going to stay the same or they're going to be opposites. So either case there. Hopefully you found it helpful, and I will see you in class.